We will talk about energy efficiency. You may know about energy as heat or power. It may include fuel as well. However, energy seems to be abstract in its nature. We find it in everyday life as a commodity. Like another ware, it is produced and after sold and bought or consumed. This happens like a flow, the energy commodity flow. Energy is expensive and its flow as a commodity is one of the most important in mankind's life. It's our major interest to keep its track preciously. This demands first measurable and reliable data, statistical data. Then it requires identifying its inputs, supply and outputs, consumption, and the inherent balance between them. Just like in our everyday cash flow. The figure left shows one generic commodity flow. The figure right emphasizes the energy balance equation. Energy in equals energy out. We will focus on energy efficiency. In a narrow technical sense, energy efficiency is the ratio of the productive output of a device to the energy it consumes. Consequently, improving energy efficiency means producing more with less energy consumption. This reasoning seems to be evident when assessing efficiency as an individual, but when applied to society as a whole, it produced in the history of the mankind and is still producing disappointing, even disastrous effects. Specialists call the Jevons paradox as a confusion of ideas to suppose that the economical use of fuel is equivalent to diminished consumption. The very contrary is the truth. Nowadays, we understand that it's our interest to live in a sustainable way. This should mean limiting economic growth. Unfortunately and simplistic, improvement of the energy efficiency drives higher rate of economic growth, which is in contradiction with the principle of sustainable development. Historical analysis of technological efficiency improvements has decisively revealed that energy efficiency improvements were almost always overtaken by economic growth, resulting in a net increase in resource use and associated pollution. This is known as the rebound effect. So, looking further for the meaning of energy efficiency, we may reveal another connotation fields beyond the technical one, namely this societal. There is our moral duty to emphasize that what really matters, it is the overall efficiency seen as ultimate social benefit. Combined heat and power plants. The power station is an industrial facility for the generation of energy commodities, called also plant. As regards the plant type, there are three categories: heat-only plants, which generate heat only; electricity-only plants, which generate electricity only; combined heat and power plants, which generate simultaneously heat and electricity. Combined heat and power plants may be of following types: cogeneration or combined heat and power, trigeneration or combined cooling, heat and power. For example, building, cooling, heating and power. One talks about one heat when it is produced in form, technical parameters that is suitable for the use intended. The need for many systems to reject heat as a byproduct of their operation is fundamental to the laws of thermodynamics. Therefore, waste heat is produced by necessity, both by machines that do work and in other processes that use energy. Power generation usually is accompanied by a lot of waste heat. Combined heat and power is about how to make an advantage of waste heat rejected. However, waste heat recovery is a matter of discussion implying advantages and disadvantages as well. Combined heat and power is nowadays an efficient and clean method to generating electric power and useful thermal energy from a single fuel source in a single integrated system. CHP is not a specific technology, but rather a combination of technologies to produce heat, power and work concurrently. The type of equipment that drives the overall system, prime mover, typically identifies the CHP system. The prime mover may be a steam turbine, gas turbine, reciprocating engine, microturbines, Stirling engines, ORC systems and fuel cells. All of the technologies nominated above convert the chemical fuel into electric power. Fuels may be solid, liquid or gases. The most suitable fuels for CHP are fossil fuels, especially natural gas, but municipal solid waste, certain industrial gases and biomass can be used as well. Waste heat recovery unit is an energy recovery heat exchanger that recovers heat from hot streams with potential high energy content, such as hot flue gases from a diesel generator or steam from cooling towers, or even wastewater from different cooling processes such as in steel cooling. You may consult in the table below a summary of CHP technology advantages and disadvantages. Of course, there are a lot of technical details for fans, but the picture below emphasizes a simple rule of thumb. Separate heat and power conventional generation efficiency is near 49%. CHP overall efficiency is near 75%. Outlook. In the last 20 years, gas turbine technology was the subject for substantial improvement. R&D is focusing on both large gas turbines and those applicable for distributed generation. Large gas turbine research is focused on improving the efficiency of combined cycle plants to 65% LHV, reducing emission even further, and integrating gas turbines with clean, cool gasification and carbon capture. For smaller gas turbine, efforts are invested on improving performance, enhancing fuel flexibility, reducing emissions, reducing life cycle costs, and integration with improved thermal utilization technologies. Microturbine manufacturers are continuing to develop products with higher electrical efficiencies. Starting with original product in the 30-50 kilowatt range, microturbine manufacturers have developed and are continuing to develop increasingly larger products that compete more directly with larger reciprocating gas engines and even small simple cycle gas turbines. Next generation of reciprocating engine are expected to penetrate on the market with higher performances, 50% brake thermal efficiency LHV, NOx emissions to less than 1 gram/bhp per hour, and maintenance cost of 0.01 per kilowatt-hour, all while maintaining cost competitiveness. R&D is ongoing toward the development of improved ultra-supercritical USC steam turbines capable of efficiencies of 55–60% that are based on boiler tube materials that can be withstand pressures of up to 5000 psi and temperatures of 1400 Fahrenheit. To achieve these goals, work is ongoing in materials, internal design and construction, steam valve development, and design of high-pressure casings. The demand for small and medium steam turbines on emerging markets such as waste heat recovery and biomass fuel power and CHP plants will increase. Buildings, energy efficiency. Building sector includes single and multi-family residences and commercial buildings. Commercial buildings include offices, stores, restaurants, warehouses, other buildings used for commercial purposes, and government buildings. Building envelope is the boundary between the conditioned interior of a building and outdoors. Building envelope components are floor/basement, walls, windows and doors, roof/attic, air leakage/ventilation. The energy performance of building envelope components is critical in determining how much energy is required for heating and cooling. Equipment of a building includes, beside heating, cooling and ventilation equipment, water heaters, thermal distribution systems, lighting and appliances, active solar systems, and recently on-site power generation. Utility services. Energy is meant as a tradable commodity, but customers in general and residential customers in special don't want kilowatt hours of electricity or gigacalories of heat. They all want utilities provided as energy services such as hot showers, cold beer, lit rooms, spinning shafts, and even more. They want cheap or at least affordable energy services. The picture below gives an overview of the structure of residential sector, comprising energy demand, services, and related end-use technologies. Conservation and energy efficiencies. Generally, conservation measures are specific measures that reduce energy demand services. Often, conservation measures imply great capital cost and but few operation and maintenance costs. Building envelope improvements are meant as conservation measures, passive design approach, While smart equipment is accounted for energy efficiency, smart technology approach. Either approach can be suitable. Whenever possible, however, it's usually better to invest in most energy efficient building envelope that is justified because it will be in place for many years, and in most cases advanced envelopes provide greater comfort. Improved comfort can foster behavior that leads to additional energy savings. Addition construction versus demolition. Non-OECD countries will face huge growth in expected construction. OECD member countries have a large stock of residential buildings, most built before 1970, that's not growing quickly and will be retired slowly. Currently, the rate of refurbishment of residential buildings is estimated to be low, at 1% per year. The basic scenarios is that the entire building stock would be refurbished within 65 years, with deep renovation between 35 years and 45 years after a building is constructed. Numerous whole building perspectives and polishing mechanisms exist, such as building performance certificates and whole building labeling programs. It's also important to consider to improve the energy efficiency of individual components. Areas for polishes actions, saving potential urgency. As you may observe in the table, there are numerous and of large variety areas for policy actions in order to improve buildings' efficiency. The pyramid of efficiency in buildings reflects the gap between current building regulations, low energy standards, and passive house standards already available for use. New technologies. The transition to efficient building envelopes can be understood in terms of three distinct stages of technological evolution. Basic building with a purely performing building envelope, single glazed clear windows, no insulation and high rates of air leakage. Typical code compliant building being constructed today in Canada, Northern Europe or the Northern United States that has double glazed, low E windows and high levels of insulation and is sealed fairly well, buildings of the future. Energy efficiency in industry. Industry covers manufacturing, mining and quarrying of raw materials and construction. Power generation, refineries, and the distribution of electricity, gas and water are excluded. Manufacturing covers finished goods and products for use by other businesses, for sale to domestic consumers or for export. Total manufacturing is divided into following key industries: food, beverages and tobacco, paper, pulp and printing, chemicals, non-metallic minerals, primary metals, metal products and equipment, and other manufacturing. The fuel processing industries and fuels used as feedstock are not included. Energy-intensive sectors are economic sectors that satisfy preciously defined energy intensity criteria provided by international agreements. Regulations cover 10 main energy-intensive sectors of industry: aluminum, cement, ceramics, chemicals, food and drink, foundries, glass, non-ferrous metals, paper and steel, and over 30 smaller sectors. Manufacturing industries are accounted for near a third of world's energy consumption and 36% of carbon dioxide emissions. The primary materials industries, chemical, petrochemicals, iron and steel, cement, paper and pulp, and other minerals and metals account for more than 2/3 of this amount. Between 1971 and 2004, the overall energy use of industry has grown by 61%. Most energy-intensive industrial sectors are complex, involving multiple process steps and producing a wide variety of products. Single energy for carbon dioxide indicator is not possible to capture such complexity. A number of different indicators are necessary to give the full picture of energy efficiency and carbon dioxide trends and levels in a country. Physically based indicators are often preferable to those based on economic measures of output. Such indicators have the advantage that They are not affected by price fluctuations, can be directly related to individual processes, and allow well-rounded analysis of improvement potentials. Conventionally, due to a lack of data, the IEA has used indicators for industry based on energy use or carbon dioxide emissions per unit of value-added output. While such indicators are good at capturing aggregate trends in energy use and efficiency, they are less suited to detailed cross-country comparisons of industrial energy efficiency developments by subsector or process, or for an examination of improvement potentials. Disaggregate indicators have been developed for iron and steel, cement, pulp and paper, chemicals and petrochemicals, and aluminum. These indicators are used to track energy efficiency progress over time and also to calculate the technical potential for energy reductions in each sector that could be achieved by moving to best available technology or best practice technology. We invite you to spend some time studying a summary of indicators for each industry sector. As well, it is interesting to overview the table showing savings from adoption of best practice commercial technologies in manufacturing industries, primary energy equivalents. Technical principles for assessing energy efficiency interventions in industry. Process integration means systematic and general methods for designing integrated production systems, ranging from individual processes to total sites, with special emphasis on the efficient use of energy and reducing environmental effects. It's not only about design methods, but also about physical arrangements such as the interconnection of equipment and process streams in an industrial plant. Systems optimization. Industrial systems contribute to production processes, including pumping, compressed air, and fan systems referred to collectively as mother systems, steam systems, and process heating systems. These systems are omnipresent in industry with applications ranging from energy-intensive petroleum refining to less intensive industries such as textiles or seasonal such as food processing. Life cycle assessment. The production of energy-intensive materials has an important share in industrial energy use. As a consequence, any kind of efficiency improvements will reduce industrial energy consumption and carbon dioxide emissions. Advances in material efficiency include material recycling, product reuse, redesign, and substitution. A full life cycle assessment of energy and materials systems is required. Industrial energy use is different from other end-use sectors as significant quantities of energy and carbon are stored in products. Additionally, materials choice affects product energy use. Therefore, it is particularly important to consider efficiency improvement options on a life cycle basis. Two types of measures are available in general. The first one relates to the efficiency of materials and product use. The second one relates to the efficiency of recovery of used materials. Energy efficiency in transportation. Transport sector includes the movement of people and goods by road, rail, sea and air. Pipelines and international air and marine transport are excluded from the analysis. The transport sector includes two main subsectors, passenger and freight. The term cars is used to refer collectively to all light-duty vehicles, including cars, minivans, sport utility vehicles, and personal use pickup trucks. Trucks are the main energy user in freight transport. Alternative terms are light-duty vehicles, LDVs, and heavy-duty vehicles, HDVs. The transport sector is a huge consumer of energy, 90% of global final energy consumption in 2007. Transport energy consumption between 1990 and 2005 increased by 37% to 75 EJ and was the fastest growing end-use sector. The associated carbon dioxide emissions followed this increased energy use to reach 5.3 GT carbon dioxide. Trends in energy use by transport mode vary significantly amongst countries and regions. The growth rate in non-OECD countries was plus 55%, in OECD countries only plus 30%. The large increase in non-OECD countries is attributable partly to the rapid growth of wealth in several major countries and partly to the increased need for freight transportation. Road transport is by far the largest energy user and accounted for 89% of total transport energy used in 2005. Non-road modes increased their energy consumption by 13% between 1990 and 2005. Cars are by far the largest energy user, accounting for 87% of the overall passenger transport energy use. In terms of energy mix, oil products as a whole totalated 99% of this consumption. Passenger travel activity in the IEA 18 increased steadily between 1990 and 2005. Car passenger travel registered the strongest per capita increases, plus 1.1% per year, while air travel plus 2.7% per year. In contrast, per capita passenger travel by buses and trains decreased slightly over this period. The level of passenger transport per capita varies widely from country to country. Transport energy paradigm. In order to assess transport energy efficiency, it's important to define and understand road transport energy paradigm. Transport energy paradigm may be expressed as a function of three main parameters, where vehicle fuel efficiency is determined by the technical energy efficiency. Vehicle travel denotes the type of travel/driving and the number of miles driven. Vehicle population is the number of vehicles on the road. As usually, International Energy Agency play a leading role in developing and promoting energy efficiency policy recommendations. 4 transport endorsements have been included in the original IEA energy efficiency recommendations: improving vehicle technology leading to increased vehicle energy efficiency, changing driver behavior to use less fuel per mile driven, reducing the distance traveled per vehicle, shifting travel to the most sustainable modes of transport, fuel efficient tires. Roughly 20% of a motor vehicle's fuel consumption is used to overcome rolling resistance of the tires, IEA 2005. The amount of rolling resistance is a function of the level of inflation of the tires and the technical rolling resistance of the tire material. Additional fuel is required when tires are underinflated. In most real-world driving conditions, tires are underinflated compared to their optimum performance level. Tire pressure monitoring systems are a valuable tool for both car safety and fuel economy purposes. Information is sent to drivers when their tires need inflation, which encourages better vehicle fuel efficiency. Concerning the technical rolling resistance of tires, tires with low rolling resistance are already available on the market. In the European Union, some modern tires have a rolling resistance of up to 30% lower than the best tires produced in the early 1980s, while the worst tires on the market have twice the rolling resistance of the best. The 3 key issues are presented: TPMS, Tire Pressure Monitoring Systems; LRRT, Low Rolling Resistant Tires; TL, Tire Labeling. Fuel economy of light-duty vehicles. The IEA recommended the introduction of fuel efficiency standards for LDVs and HDVs in the 25 energy efficiency recommendations. Although vehicle labeling was not listed separately as a recommendation in the measures, it's an important complementary measure to fuel economy standards. In April 2009, the European Union adopted the regulation setting emission performance standards for new passenger cars as part of community's integrated approach to reduce carbon dioxide emissions from light-duty vehicles to reduce carbon dioxide emissions from passenger vehicles. Average emissions from new passenger vehicles sold in European Union have to reach the 120 gram carbon dioxide per kilometer target by 2015. Improvements in motor technology will reduce average emissions to no more than 130 gram carbon dioxide per kilometer, while complementary measures will contribute a further emissions cutoff up to 10 gram carbon dioxide per kilometer, thus reducing overall emissions to 120 gram carbon dioxide per kilometer. You may observe the limit value curve of the passenger car regulation in figure below. Eco-driving. Optimizing gear changing. In 2009, the European Union adopted the regulation EC 661/2009, which stipulates the mandatory fitting of a gear shift indicator (GSI) to all new passenger cars with manual transmission as a part of European strategy on reducing carbon dioxide emissions from road vehicles. The GSI is an indicator which displays shifting up or down signs on the instrument panel to ensure optimal gear changing and thereby improve fuel efficiency. It's one of the in-car feedback instruments recommended by the IEA to promote fuel-efficient driving. Avoiding vehicle idling, e.g. by turning the engine off when the vehicle is stationary. Avoiding rapid acceleration and deceleration. Driving at efficient speeds. The most efficient speed for most cars is between 60 km per hour and 90 km per hour. Above 120 km per hour, fuel efficiency falls significantly in most vehicles. Reducing weight by removing unnecessary items from the car and reducing wind resistance by removing roof attachments such as ski racks. Model shift. An important policy goal in transport energy efficiency is to shift passengers and freight from roads to more sustainable modes of transport such as bicycles, efficient public transport, shipping and rail, called modal shift. It's estimated that the benefits significantly outweigh the cost in many cases. Policies for passenger modal shift generally include improving public transport services and infrastructure and increasing its attractiveness to potential passengers through information campaigns and improving practical features such as integrated ticketing, real-time travel information, and lower fares. Shifting freight from energy-intensive modes such as road and air to rail and shipping should be a priority for many countries. Freight road transport has significant external costs, even compared with light-duty road transport, particularly in peak hours, and is the source of substantial physical damage to road infrastructure.